I'm typing up. Okay.
All right, everyone, 10-minute break. 10-minute break, so back on track. All right, for the double lecture, I know it's painful. Not a lot I can do about it. Looks like it's kind of really good for you on Wednesday while you're preparing for it. So, again, just to remind you that I will have something like this on the test. These partial volume questions, there's a lot of, I know that question didn't look like much, but there's a lot of really simple, like number games you can play with them to ask questions based on partial volumes. If I end up putting one of those on there, I'll show you how you actually work those. I'm not going to bring up partial volumes again, just maybe a little bit for now, but not really very much. So if I end up putting one of those, I'll work a problem on Wednesday. Other than that, okay, so again, remember the point here is that for vapor water, and I use the word vapor because while water vapor is gaseous water, and there's plenty of gaseous water in the air, when I say vapor, it's generally coming from a cup of water underneath it. And I'm telling you that vapor, when mixed with B, has a certain change in G up there. And of course, you have to consider what happened with B as well, with that vapor that came from putting like two cups close to each other. And those vapors, of course, they mixed according to this guy here. And I'll show you in a minute that they definitely mixed. And so there you go. Now, when I did the magical trick of dividing by N, it became chemical potential. And don't forget that, so if the chemical potentials, if this thing is in equilibrium, then the chemical potentials had to be equal, and so therefore if they changed, then they changed equally, because they're the same thing. Sorry, I didn't use that. I didn't use that. So again, chemical potentials before and after are the same. Then after they've mixed, the chemical potentials after are the same. That means that the net difference is the exact same thing. Okay, so likewise you can, so this gives me a formula for changing chemical potential of the liquid. It's the same as the chemical potential, change chemical potential of the liquid. It's obviously pretty much the same thing as delta G because I'll just mix 1 mole with 1 mole. And remember, delta G divided by 1 mole is the chemical potential, but it's still the same number, right? So I get chemical potential and G at the same time. And I'll be friendly, I'll always just mix a mole so we don't get too confused about what's what. And so now I've taken a vapor formula, and now I've got a formula for a liquid. So, and to get the other suckers, H, S would be the ones you want. You do a similar types of calculations. I'll do some examples of that. One last bit is, let's say that I'm going to just formally say that this vapor phase equation is that of the liquid phase. So I'm going to start again with all this delta mix G. And okay, so our moles come back. I don't have mole fractions because this is not per mole. And so the way, again, let me read this equation and in words a person can understand. What I've done here to measure what the mixing G of the liquid was, and again, I'm doing this at room temperature, 1 bar pressure. I've got water and I measured its partial pressure. And I've got ethanol, I got a cup of ethanol, and I measured its partial pressure, which are the pure partial pressures. And then I mixed them together, and I have some kind of device that measures the partial pressure of the water after, and the partial pressure of ethanol after, separately, maybe some kind of mass spectrometer did that. And then I can fill out this equation. Now let me do this. I'm going to multiply by n, and I'm going to divide by n. So this is a little bit of a trick. Where n is the total number of moles. Just in case you get confused, I mean that whenever I put n, I'm talking about two things. It's obviously it's always the total. In case you get a little lost with those. Okay, so there's that. Here, let me show you another thing I can do. I can say that the partial, I'm using basically Dalton's law. Remember this one? This is basically a Dalton's law that you can just treat vapors, which are gases, as though they are independent of each other. And for perfect gases, that's absolutely correct. They don't interact, they don't collide. And PB, chi B, PB star. So if I get rid of half the vapor, because I mixed the solution from which they came from by 50-50, then I would have half the partial pressure. And that's again a Dalton's law argument. So that means that this is now, let's see, that's the mole fraction of A. Let me factor a little bit. nRT. What I've got is chi sub A and natural log chi sub A. What's wrong? P sub A over P sub A star. Well, they're both stars, so that's a 1. Plus chi B, Ln chi B, PB, PB star. They're both star because I just introduced Dalton's law. And then that simplifies a little further. nRT, chi A, Ln chi A, plus chi B, Ln chi B. Okay. So as we do all these mixing things, you're going to see this a hell of a lot. And also notice that, let's see, it may not have been obvious, but this is actually all coming from entropy, by the way. Because I recognize that formula from which I started from right up there. It looks like entropy times temperature, essentially, right? Because I have natural logs of things. And whenever I see natural log, I know that that's entropy somehow showing up. Maybe I don't quite know how. And that's true of any type of physical equation for reality. You see natural log, entropy. Entropy is doing it. Because remember, K, Ln, number of microstates, which is on the test. In a simple way, as I promised, I wrote those questions like knights on a chessboard. That's not the question, but it's like it. So anyway, because entropy is natural log of microstates, ever I see natural logs, I know that's entropy doing something. So just remember that. So now I can define what makes an ideal solution. And so, as I mentioned, I don't like this material so much because let me go ahead and warn you that I took this idea for vapors mixing, and now I've just basically said divide by a mole. It's now chemical potential, and it's the same for the liquid. And since I divided by 1 mole, it's still the same damn thing, right? So the problem actually is here. Now this is fine for a vapor. Dalton's law works for a vapor. This is no more wrong than PV equals nRT, which isn't really bad at all, to be perfectly bloody honest. So this is no worse than PV equals nRT in terms of vapors. But now I'm going to say that it's just the same damn thing for a liquid, where if I'm mixing 1 mole of water and 1 mole of ethanol, half Ln and a half Ln and a half. And then I'm at 25 degrees C, and I have 2 moles, and I have R as R. Right, now here's the problem. This is, for the vapor, perfect. For the liquid, a massive approximation. And it's because these are the mole fractions in the vapor phase. Okay, if that's true, then that's fine. But if you want to say that those are the mole fractions of the liquid, when I just did a second ago, I said half and half for 1 mole water, 1 mole ethanol. This is actually a very bad approximation, actually extremely bad. And so this is why I don't like this material so much. And I'm going to throw correction factors at this. And where do I get the correction factors? That's what I was telling you before, from experiments that say, no, you didn't actually measure the right thing. And what do? We actually throw the correction factors at these. They're called activities. You heard that before, right? Remember, activities are, you talk about concentrations of stuff in solution, but you were told as freshmen, well, those concentrations aren't really quite right. What you want to do is multiply the concentration times a activity factor. Right. It's a correction factor. It's an uh-oh, it doesn't work. Now, we know why they don't work, but we can't predict them ahead of time. So anyway, that's ahead. Now, ideal solutions don't have a problem. Ideal solutions are defined as this works perfectly. And what that means is that, or I'm going to stick with A and B, have one, same volume, same molecular volume, and two, same molecular interactions. Okay, so why didn't I call this a perfect solution like a perfect gas? Well, it's a liquid. It's a liquid, so you can't ignore molecular interactions. It's why you have a liquid to begin with. Now, you do with the gas. Gases don't attract each other, right? That's the 8-parameter in Van der Waals equation. But the 8-parameter in Van der Waals equation for a perfect gas is 0. So you say gas molecules don't interact. Well, you absolutely cannot do that for a liquid, because that's why you've got the liquid together. But you say that A and B interact exactly the same. So that's, again, like hexane and cyclohexane. Ethanol, water, not so much, because of the disruption of hydrogen bonds. Same molecular volume. Okay, again, O-xylene. O-xylene and P-xylene, basically the same thing. Same volume. So with that, these equations, especially this simplification, is just fine. And let's go over why. So let's do the first one, consequences. Okay, so an ideal solution, we're not going to call it perfect. Of course, volume isn't 0. So that's why we don't call it perfect solutions, we call them ideal. Because you don't forget their interactions, you don't forget their volume, like you do for perfect gases. Okay, consequences. All right, let's look at 1. Stipulation 1, they have the same volume. So what's the change in volume? I added 18 mils of A and 18 mils of B, and they have the same molecular volume. What's my total? It's 18, right? I heard one of you say, 18 plus 18 is 36. So is this 36? Is it 36? What is it? Huh? Start talking, someone.
0.
0, right. I'll give it the volume. I'll give it the unit. It should be a meter cube anyway. Right, 0. Remember that this is the difference from what you thought you should have measured. And again, 18 mils plus 18 mils of whatever, your instincts are going to say you have 36. That's perfectly logical, but you didn't measure it 36. You were a little off, maybe a little high, maybe a little bit low, so this has a volume value. That would not be an ideal solution because the molecule's volume is exactly the same. There is no mixing. You got exactly what you thought you should get. Okay, let's do U. This is consequence 2. All right, this isn't going to be particularly difficult to figure out. It's 0. Nothing. You are nothing. Anyway, so those are 0. And so now, and again, this is because the molecular interactions are the same. Now let's do the mixing enthalpy. Okay, that's going to be the mixing U. Sorry, mix change in chemical potential plus the mixing of, right now pressure's constant. We're going to get 1 bar. So that PDV, so that VDP term is 0. Then I've got PDV, which is this term, is now 0. All right, I won't ask because that's stupid. Everyone's tired anyway, so 0, P times 0, okay? And so that means that the only thing you really have left is mixing entropy. So I'm going to do mixing entropy, and again, I'm going to cast this, oops, mix, I got to write mix. Remember the process, delta process what? Okay, and I'm going to do NR ln of, let's see, it will be the final volume over the original volume of A, and so that B is the volume of A plus B. And then you can't forget B. B is just as good as A. And so BB, painted myself in a corner. Sorry, I painted myself in a corner. I'll have to go to the other board. Here, sorry about that. Well, your notes are better than mine. So there's that. And let me do another little step just because it's going to make our lives easier. Right now, I'm looking at that, and I'm a little flummoxed about what to do next. So let me flip some things over. Sorry, I'm not writing this continuously. I'm going to just put a minus sign, so that way I can flip V over VA, because that is just more familiar to me. I think I know what that is. And minus MD R ln dV over the total volume. Now here's the trick. If they have the same molecular size, and I have a mole of A and a mole of B, I mix them together. So the mole fractions of each is 1/2. All right, now, let me just slow down for a second, think logically, all right? I mix 1 mole of A and 1 mole of B. Their mole fractions are 1/2. The total volume is 36, and this guy was 18. 18 over 36? 1/2, the same as the mole fraction, same as B. And it will be universally true that Ln mole fraction mole fraction. There we go. Yep, so, yeah, there we go. So I think we'll do something with those. Okay, so now delta G is delta mix H minus T delta mix. All right, we already said that guy's 0. And so I multiply this by T. And I've got delta mix G is now n sub A RT ln chi sub A plus n sub B RT ln chi sub B. And I'm not going to write this, but I'm going to multiply by n over NA. And sorry, I'm going to multiply by n over NA, so I'm going to cross out MRT. Now I've got chi A ln chi A plus chi B, because I've already done this. So don't think this is a mystery. I did this just in the last hour. There you go. You have trouble seeing it. And let me write this. Go. Right here, that's the end result. That's the guy I'm trying to get to. So, anyway, now the important thing is that this is identical to, it's right here. They're identical, right? So the important part here is to show you that where this comes from, as I said a minute ago, this comes from entropy, and entropy alone. Because for an ideal solution, delta H is not 0. Now, we're going to take into account that delta H is something other than 0. It can be positive or negative. And you know when liquids mix, sometimes they get warm. And occasionally they get cold, but that doesn't happen as often. And we're going to have, and that's a problem, because I made it 0. So later, next Monday actually, we'll start introducing correction factors for delta H mix. And we know what those corrections are from, unfortunately, having to do the experiment. And having to do the experiment, and then we know what the correction factors are. Okay, now tell me, is this always positive or negative? Okay, NRT, brainless. That's a fraction. Ln of a fraction is negative, right? So nothing, everything positive, positive, negative, positive, negative. Well, remember, negatives are like winners. They, like Charlie Sheen on, you know what? On his tiger blood. It's negative. Negatives always win. So that makes the whole thing always negative. Now notice that means ideal solutions always mix. Yet you just saw a minute ago that solution. Take a look. You see that solution at room temperature does not mix. So again, that's why I don't really care much for this stuff. And then the fact that things don't mix, again, will come through correction factors by this guy here. And we're going to get into that. Let me summarize. Let me say first, for ideal solutions, delta mix G is always negative. Delta mix S is always positive. Delta mix P is 0. And delta H mix is 0, but these are defined. Okay, so there's nothing special about those being 0. It's how I got to these equations for S and G to begin with, by saying they're 0. So that was the first step. I didn't have something deeper, some deeper knowledge or mathematics that said this. I just started out with this. So remember that. And that obviously isn't really correct. So, and then also let me show some other little factoids at 25 degrees. You know what's funny is I was actually reviewing a paper, and this person was talking about making binary materials like solid state, and they said that there are certain energetic limits that one runs into when maximum entropies, maximum delta G's, when you mix solids together. Sorry, let me get rid of this for a second. Sorry about that. I'm going to take myself into a corner for the joules per mole. So this person said, well, there's maximum entropies that can be achieved, and there's maximum delta G's that can be achieved. So this is T delta mix S per 1 mole. I won't say that. And of course, you just see that this is obviously minus that, and that's delta G, delta mix G on the bottom. Sorry, they should be the same. I'm just not working my pen very well today, obviously. So my point of that little story was, this guy actually drew this, but he had the numbers completely wrong. He had like megajoules. And I was like, okay, nRT half ln half plus half ln half is 1.7 kilojoules per mole. This guy is about to write a scientific paper in one of the biggest journals, and he could not get this right. And he was off by factors of 1,000. I thought it was funny. He didn't. And then here, there's a generalizable formula. So I've done A and B a lot, so I'll toss this up here in a second, just to make it more general. And I'm not going to use this again, it's just, this is how you tend to see it. nRT is just that if you have more than one thing, you need to just put a summation, and you got chi sub I ln chi sub I. And of course, the same for entropy. Where am I doing G again? S. And of course, you see, you just lose the, you just miss the T. And of course, you have a minus sign. Sorry, flubbing up today. Just kind of tired. There we go. Here. So here, so you can write that down. You can see it, sorry. Here it is. I don't care. I'm always going to stick to 2 things because it's too hard not to. Besides, if you understand 2 things, you got 3. I'm just testing your calculator ability. If I start asking questions about 3 things, I'm not going to do that. Because if you understand 2 things, it makes me understand it well enough. Okay, so next bit is, how do I put this? Let me say ideal. Ideal solutions follow, this is hard to pronounce, Rayou's, R-A-Y, I have to, R-A-O-U, Rayou's law. Reynolds law. So the idea is that I want to see how vapor pressures change as things mix, because I have great thermodynamic equations for vapors because they're gases. Now you see why I focus so much on gases. And now I just want to say that the composition of the vapor is the same as the composition in terms of mole fraction as the liquid. Now that's where I'm telling you that it's completely screwed up. That can be massively incorrect. And that's actually makes the enthalpy doing that. All right, so again, let's talk about vapors. And let's do a composition diagram. So pressure, these are vapor pressures. And I always like to call my solvent B, and I usually like to put the x-axis as belonging to B. And so let's look at the pure partial pressure of B. And that's what it is. And I know that if I have all B, that I have my little sniffer that's going to measure the partial pressure, and that's what it is. Now at 0 B, I should not have any vapor pressure of B, so it should be at 0. Reynolds' law says that it's going to be a straight line. Ideal solutions will make a straight line with composition. That's not the worst straight line I ever drew. There we go. Okay, that's a straight line. And partial pressure of A, let me move this out here. Partial pressure of A is there, and of course I know it'll be, this is 0 here. It'll also be a straight line. And then the total will be the line that connects the top of the two. Sorry. There we go. There you go. And notice that, again, the point of this is, it's saying that the partial pressure, sorry, I'm a little flubbered on this guy. I always get flubbered because I just don't like this stuff, because I know it's inherently correct. So you assume chi's of the vapor equal chi's of the liquid. Okay, so making that assumption. And again, this is like xylene plus toluene, hexane plus heptane, methanol plus ethanol, things that are just trivially different, things that I don't really even care to mix. So we often are interested in making mixtures of things that are very different or reactive. Better yet, that's what we're trying to get to. But again, remember, I have to mix things first before I get them to react, so that's what we're doing this for. So my point is that very few things follow Reynolds' law. And notice Reynolds' law is based on an approximation. Why does he get a law? I kind of hate the guy. I don't even know him. Kind of glad he's dead. So why is it wrong? Actually, I don't know anything about him. I know all that Gibbs' father, Gibbs, and these other guys. I don't know this guy. So it turns out that Reynolds' law is going to work pretty well once you've got mostly pure A and mostly pure B. But now let's have a container. Here's our beaker. Look, I even drew that. We've got our container, our little beaker, and in it is a solution. And these little molecules here. And of course, these little molecules occasionally, they jump out into the vapor phase, and that's where my sniffer sniffs them. Okay, now this is perfect. The partial pressure is the pure partial pressure, but nothing's mixed, so what do I care? Now add, so this is B, that's a solvent. Now I'm going to add a solute. Notice I didn't draw it the same way. It doesn't have the same volume, it's not going to interact the same. So what's going to happen is that some A, now we will let them mix. Some A is going to come into solution, and here it is. Now the problem is that it's getting in the way of B. A, the square, is getting in the way of the solvent B, because some of it floats on the top. Now if all things are equal, if this is an ideal solution, despite the fact one's square and one's round, then the composition of A in the body of the liquid is the same as the composition at the surface. That sounds very reasonable. It'd be kind of the logical first step to think about. And so, therefore, the vapor pressure, so what happens is, this guy would have gone into the vapor phase just because they do, but it didn't because this one took its place. Right? Now, that means that the partial pressure of the solvent has gone down simply because it's simply not accessible to the surface anymore. It's just that simple. And A is taking its place. So A is taking its place. So my sniffer now tells me that there's a certain finite partial pressure of A, which is perfectly sensible because I just poured some A into the solution and they've mixed. And so this ought to work for very dilute solutions. But you know that once I start adding more and more, they start interacting with each other more and more, and this can set things off a bit. Here's problem one. Problem number one. So these are the problems you're going to get when things start to really interact. I'll draw the beaker. Here's the solution. And as I add more A doesn't really like B, and A has a lower density. You know what it's doing? It's like when Juno body slammed Zoe, my cat, last night, causing an absolute uproar in my house. It's on top of B. It's not letting B out. I didn't even add that much more A, but now B can't get out of the beaker. So it's screwing with B. Now I'm going to just draw the vapor pressure of B. And one of those little diagrams again. And so here's the pure partial pressure. Now, again, this would be ideal. I'll just say ideal. Now I can see that as I add more A, and it's going to be a little jerk and get on top of it, at first it's not much of a problem. But as I add more A, the problem's going to get compounded. So I might see deviation. Sorry, that's such a shitty line, but anyway, you get the point. At first, I don't think that it's going to be really very different at all, but eventually it does. It does start to matter, and it gets a lot off. Here's another possibility, problem number two. Problem number two. And here's my beaker. You probably already figured what that is. That is A is getting on the bottom. A sinks to the bottom. And what's that doing? It's actually, so these are non-idealities. They don't like to interact with each other. A is actually starting to push B out because it doesn't like it. They don't interact correctly, like my two freaking cats. And they fight a lot. Pissing me off. Anyway, so let's do the mole fraction B. Sorry, you probably assumed that. That was good. Okay, here's ideal. Here's the ideal line. And if this thing is trying to push it out of the beaker, well, I imagine the exact opposite. Now, at first, again, it's fine. Everything's okay. But it rapidly gets to be not okay. And so you see a deviation like that. Now, in your mind, of course, A is the same thing. Remember, we're on the left side, and A is the solvent. So, so now how do you treat that? Now, this is the part that really makes me want to vomit blood. So remember, call the hospital if I actually do it. Don't call the hospital if I'm badly prepared. I don't know if you all saw that news story. There was a teacher at some college somewhere started saying nonsense words. And maybe he was a joker like me, and all the students started laughing. But one of the students realized he was having a stroke. And then he died. No, I'm kidding, he lived. The student saw that he was having a stroke. So I guess I'm the boy who cried wolf because I do it all the time anyway. Okay, so how do you fix this? And again, this is something I really present. This is called Henry's Law. Henry's Law. Now, all Henry's Law is a mandate on a boo-boo. Now, these curves here are deviations from ideality. They're saying Raymond's law actually really doesn't work. It's okay when I have a lot of one thing, when solutions are very dilute, then they're kind of ideal. But when you start mixing things up pretty good, then they're really not. And that's actually more often true than not. This is more reflective, the curvy curves are more reflective of reality. Henry's law says, okay, well, all right, so I know that doesn't work. Let's make up something else. And that's why I hate this stuff. Let me do the two scenarios. So let's go back to scenario number 1. And I'm going to have to kind of exaggerate this because I screwed this up a lot. Here is ideality, Raymond's law. Here is the uh-oh. Now, what you do with Henry's law is you make a projection. Now, again, Raymond's law is good at high concentrations. This is obviously 1 and 0. At high concentrations, Raymond's law is fine. And at low concentrations, Raymond's law is a failure for most things. So what you do is you project to this point, and you call it K. Again, this is the linear extrapolation at low concentrations. So Raymond's law says this. The here part, it says that that the partial pressure of B is equal to the mole fraction of B in the liquid state, which times the pure partial pressure. Again, a sensible first thing to go to. But Henry's law, knowing that at dilute conditions, that's not so good, does this. You're going to love this. PB is equal to a mole fraction of B times K, where that's the Henry's law constant. And let me do the other scenario as well. I shouldn't waste your time with this, but anyway. Okay, so of course, situation 2 was this. I'll do it quick. When the A is trying to push B out, B star. There you go, and that's when. Oh no, wait! I got those reversed, didn't I? Sorry. I just like this one better. Here we go again at high concentrations when B is pure, Raymond's law is fine. At low concentrations it's not, and there's our K. So, okay, let me work at a problem, an example problem with Henry's law constants. But again, let me first back up again and show you why I really hate this stuff. Because these straight lines are rated. Broken class? Yeah. Okay, have fun fixing it after class. Anyway, so Raymond's law works for just a pathetically small number of things. That's the straight lines here. Reality is the curvy lines are correct, and that's because when you mix things, there is some enthalpy, right? And that means that you're not ideal. And the non-idealities show up generally in this kind of way, where partial pressures are not linear functions of partial pressures of vapors for which we get our equations are not necessarily reflective of the composition of the liquid. So the mole fractions of the vapor are not equal to the mole fractions of the liquid, and that happens because you actually do have an enthalpy of mixing. As now we see for these straight lines, they're 0. Now, Raymond's law says nothing's wrong, but it actually is. So Henry's law is simply a fix. It just is a constant that we determine for every 2 pairs of solutions to make this equation work. And it's done by experiment. You see why I don't like this? Because physical chemistry, let me tell you, the ideal is that there's no empirical factors. Everything is known by the fundamental, I have R, I have KB. There are fundamental physical constants, and with those fundamental physical constants, I figure all this out, the curves, without having to do an experiment. That's the ideal. And Henry's law, Raymond's law is not really good about that, and Henry's law is even worse. And we even call them laws, which is stupid. Anyway, But Henry's law is kind of relevant because it describes one thing very well. Henry's law describes gases dissolved in liquids. So I'll have one or two homework questions on that. That one is actually kind of important. So let me give you an example. K N2 and H2O is 1.56 times 10 to the 5 kilopascals, kilograms per mole. Yeah, there you go. Okay, and the question, that's off. The question is, how much N2 is in 1 kilogram of water? Okay, so you engineers, you're looking at power plants, and this is a thing that you have to figure out, and you look up Henry's law, and this is all the information you get. Now, this is one of those times that hopefully you'll see why I'm obsessed with units. Again, I got this off Google. This is all I could find. I don't know how to work this, but if I know units, I do. Because it's not really saying kilopascals of what, kilograms of what, moles of what. It didn't tell me that. But this is what I found on the internet, exactly this. Now, for whatever reason, your ass is going to get fired unless you come up with this number. So manipulation of units is going to help you solve that. Now, so let's walk through it, and then we're done. We're already on time. I got to figure out how to work this number, and this is all I've got. I know I'm dealing with how much N2 is in 1 kilogram. So let me put that another way. How much nitrogen gas per kilogram of water? Now again, I have to manipulate this thing. You can imagine I'm either going to multiply by something or I'm going to divide by something. Whatever I do, I'm going to have to come up with something that's per kilogram of water. So remember that. The question is, how much nitrogen per kilogram? I've got to come up with something like moles of nitrogen on top and kilogram of water on bottom. Now, again, this is what I found on the internet. Is this going to multiply? Is this going to be something that's a multiplicative factor? Or is it going to be a numerator or a denominator in a division equation? Again, I'm just trying to figure out what to do with this number. Now, I have to get per kilogram. So what do you think that kilogram represents? Kilogram of water. Right, it's the kilograms of water. Right, so am I going to multiply this by another number? No, it's going to be a numerator or a denominator. Right, it's going to be the denominator of something. All right, so now I've got that much figured out. Now we've got two other units to figure out. And of course, those are going to tell me what's on top. All right, now I'm going to see, it makes logical sense. Again, the internet will tell you, that's kilograms of water. So I know that it's going to be on the bottom, but then something's on top. Now I've got to figure out what that is. Now, what do you think the mole represents? Because I've taken out my water. Water's done for. A kilogram of water, I know how many moles that is. I think it's 55, but anyway. 5,500. Anyway, moles, what do you think the moles is? What?
Hydrogen.
So what you said, hydrogen? Nitrogen. Right, and now it's on top. It's on top. Okay, so now I see that this is going to return me moles of nitrogen. So I'm almost there, but I still haven't quite figured out what's on top yet. Kilopascals. All right, now I open up a soda can. What does it do? Hisses. What's it hissing? Which gas? CO2. Okay, that doesn't matter. They pressurized it, right? Why did they pressurize it?
So the gas dissolves.
Right, so more gas dissolves and it's fizzier. So what do you think's on top? The pressure of the gas. Well, we'll make it atmospheric pressure. We'll make it 1 bar. Sorry, I was supposed to add this. At 1 bar. So that's 100,000. So 100 kPa. And unfortunately, I don't have a calculator in front of me, but that's going to give you X moles of N2. We'll actually work a couple more problems next time. So anyway, Henry's law sucks. but I really hate it. I don't know why I'm so angry all the time. But it is useful for this stuff, knowing how much gas is dissolved in liquids. And a lot of you may end up working in the soda industry, so this is kind of useful. And by the way, who thinks Guinness actually carbonates with nitrogen? Does anyone think that? Remember that? That was an urban legend when I was your age. No, it doesn't. They use CO2. And we'll figure out, that's actually a problem set question where you figure out that Guinness does not carbonate with nitrogen gas because it can. I'll see you all on Monday, all right? So that's fine. Email me if you have problems.
Did you leave it? Did you leave I told them they were missing between
that's the time I gave, I returned it.
or 5
But this way,
Don't look at
take it back with Thursday because by now we have to look for it.